All right. So now I want to prove this lemma in the case when A is constant, and I will add some more simplification, which is I will suppose that A is symmetric. So meaning that A alpha beta is equal to A beta alpha for any alpha and beta. So so this is not a bigger simplification, it's just technical. It's if I don't have a symmetric function, I have to consider the corrector for the A star, so the transposed matrix. But I don't want to do that, so I just stick to asymmetric. So what you already know from L2 boundedness is that A of x over epsilon k gradient u k converges weakly to some psi in RD in L2. So the goal of the proof is to identify this psi and to show that it's equal to A bar gradient U bar. So so I will so the method of proof goes back to Tartar and also the work of Murat in the late 70s, and it's called oscillating test function. So the idea is to take a function, test function, not phi, but a test function which is oscillating and which in some sense mimics the behavior of the solution. So instead of taking, so I fix a beta in one D, and I want to identify psi beta, so the beta component of psi, which is a vector in R. And the test function I take is phi of x times x beta, so this is a function, plus epsilon k beta x over x. So I have a compactly supported infinity function phi, compactly supported in V01, times this function, which is oscillating function and which is A linear. So testing against this function, I obtain the integral over B01 of Ax over epsilon k, gradient UK, gradient phi times x beta plus epsilon k. So this is epsilon k. K beta x over epsilon k. Okay, so this, so I test against this test function, and this is when I integrate by parts, and this is when the gradient falls on phi is equal to minus the integral over B01 of Ax over epsilon k, gradient UK, phi times gradient x beta plus epsilon k, k beta x over epsilon k.
So phi is the element of C infinity and compact, which means topologically closed area or closed contour, which means topologically speaking, if we don't think about specific metrics, this is a periodic.
Yeah, there is no question of periodicity here and topology. So it just compactly supported. It means that the support of phi is contained in the Bldg 1. So here I have the left-hand side and the right-hand side, and I will pass to the limit in the left-hand side and in the right-hand side. So in the left-hand side, it's actually quite easy to pass to the limit because here I have that this converges to xi weakly, and this converges strongly to x beta. Because the epsilon k beta goes strongly to 0 because of the epsilon k. So this goes strongly to 0, and this goes weakly to xi. So I can pass to the limit, and I get that this is the integral over B01 of xi gradient phi x beta, which I can rewrite if I integrate by parts this derivative. I can rewrite this as the integral over B01 of psi beta phi of x dx. I guess there is a minus sign. Yeah. Okay, so now for the right-hand side, I integrate by parts once more. And so I will first put the A on the gradient. So this is where I use symmetry. And I integrate by parts once more. And this is where I want to use that this function is A harmonic, is a solution of the equation. So we'll get that the right-hand side is equal to, so plus UK so AK A of x over epsilon k gradient x beta plus epsilon k beta x over epsilon times gradient phi. And this now you can use the fact that UK converges strongly and this converges weakly. So it's strong times weak convergence, so you get the convergence. So this converges to U bar, and then this will converge to A bar. So dot beta, meaning that this is their beta colon of A bar times gradient phi. And now if I integrate by parts once again, so I get the, I'm a little bit confused with the sign, but I guess here I get a minus. Yeah, so I get a minus the integral over B01 A bar gradient U bar beta and phi of x dx. Okay, so finally, comparing the left-hand side and the right-hand side, you will get that this a bar, so you will get that xi beta is equal to a bar gradient q bar beta, which is the result which you needed to prove. So this idea of oscillating test function is quite beautiful, and you see that you get the result immediately. There is another way. If I had the AK instead of the just fixed A, I would need to use diff curl type lemmas. So you can also take advantage of a diff curl type structure. But here, in this case, in the case when A is fixed, there is no need for such a tool. All right. So now I'm ready to state the result about the uniform estimate. So the theorem, which goes back to the work of Avellaneda and Lin in '87, and which is their uniform Lipschitz estimate. So, so there exists a constant C, which depends on dimension, lambda, L, and M. So I will tell you in a minute what is M. Such that for all A in this A per lambda L, so now I will, in addition, assume that A is Hölder continuous. And this is just in order to have a result up to the scales smaller than epsilon. So I will just state it in the result, but I will focus on scales bigger than epsilon. But in order to state a result about the whole Lipschitz estimate, I need some smoothness about A. So we'll assume that A is C0 mu. So actually, constant will also depend on mu. So Hölder continuous with exponent mu. And I will assume that the Hölder semi-norm of A is smaller than M. So M is the constant appearing here. Then so there exists a constant such that this, or we have the bound. So for all solution U epsilon 2. So do I still have the equation? So I will denote this equation, let's say, by star. So to the elliptic equation star, we have that gradient of U epsilon in L infinity of the smaller ball is controlled by C times U epsilon in L2 of the bigger ball. So I have a control of the Lipschitz norm of U epsilon by in the smaller ball by the L2 norm of U epsilon in a bigger ball. And this is uniform in epsilon. So so for all epsilon, And the uniformity in epsilon is, so I will keep the equation. So the uniformity in epsilon is not at all trivial, because it's if you apply the classical regularity theory. Classical regularity theory involves some regularity of the coefficients. So the constant, if you apply classical regularity theory, involves this. So it will involve a of x over epsilon in C0 mu, for example. So you will get powers of epsilon coming out if you apply classical regularity theory. So this is really a consequence of homogenization. It will not hold for arbitrary functions, or arbitrary coefficients A. So let me just sketch the proof before doing it precisely. So the sketch of proof goes as follows. So there are three steps. So the first step is the improvement of flatness. So this is actually the step where the compactness argument is taking place, and where you have the where you use the regularity for the limit equation. So you know that you will, for epsilon k, for epsilon going to 0, because of this lemma, you will converge to the homogenized equation. For the homogenized equation, you have more improved regularity, because it's constant coefficient, and then you need to go back in some contradiction argument. So step 2 is iteration of step 1. So in step 1, you get an estimate uniform in epsilon, but only at some intermediate scale. So let's say 0, 1/2. You will get an estimate at some scale theta, some intermediate scale theta, but uniform in epsilon. In the second step, you need to reiterate this estimate in order to get the estimate at some scale theta 2, theta 3, etc., etc. In order to get it at all scale, the row between epsilon and 1/2. So the limit, so the smaller scale for which you will be able to prove some estimate uniform epsilon will be epsilon. So we'll see why in the proof. And step 3, so you iterate down to scale epsilon. And step 3 is finally below scale epsilon, you apply a classical regularity. So this is the blow-up step. Okay. So one key tool in order to prove this Hölder type estimate, Schroeder type estimate. It's something we already encountered, which is the characterization of Hölder continuity in terms of integrals. We saw this in the first lecture with Widman's whole theorem trick, where it was used. Now I will state the precise result, which we'll use. So it's I think it's mainly due to Campanato. So if omega is a Lipschitz domain, then for all alpha in 0, 1, so up to 1, C0 alpha is equivalent to L2 lambda. So with lambda is equal to d plus 2 alpha. So this belongs to d plus 2. And L2, so this curly L2 lambda of omega is equal to the set of functions which are L2 on omega. And so that the following semi-norm is bounded. So the supremum over all points x0 in omega, rho bigger than 0, of rho minus lambda, omega intersected with bx0 rho, of the oscillation. So the difference between u and u x0 rho square. So the u x0 rho, because we deal all the time with means, we have several notations for means. So one notation is int bar for the mean. Another notation is u between brackets. So u x0 rho means the mean of u over px0 rho. Okay. So so I'm comparing the u to its mean on this board. And this here is also 1 over rho 2 alpha int bar over omega intersected with b0 bx0 rho. Up to a constant dependent on the omega in dimension of u minus ux0. Okay? So very often I will just use 1 over rho 2 alpha in bar. Okay. So this characterization is very convenient because this enables to deal with integrals, and for example, Cacciopoli inequality, or every time we test the equation against some test function, we deal with integrals. So this integral characterization is very useful. And let me notice that it holds for any p in 1 infinity. So we'll need a p different from 2 this afternoon. So if I replace these 2 by p, then I have the same characterization, except that the lambda will live in so lambda will live in d plus p. Okay. So, but for this morning, I use only p equal to 2. All right. So, and the proof of this lemma, so I will not do it, but it's quite elementary. It's basically only Lebesgue's differentiation theorem. Okay, so any questions so far? Before I enter the details of the proof of the Lipschitz estimate. Okay, so as I told you, I will focus on step 1 and step 2. And step 3 is just more classical, so I will skip it. So, so step 1, the main lemma is about the improvement of flatness. So I'm given an alpha in 0, 1. There exists theta in 0, 1/2 and epsilon not in 0, infinity, such that for all A in A per lambda L, for all epsilon smaller than epsilon naught, so for all positive epsilon, and for all weak solution U epsilon to star, so the equation with oscillating coefficients. If the mean of U epsilon square on B01 is bounded by 1, so I take a family of solutions and I assume some compactness on this family of solutions. Then, so the mean over B0 theta of U epsilon, and now I want to prove C1 alpha improved regularity. So to prove C1 alpha regularity, I will compare U epsilon to a polynomial. And I'm not comparing to a real polynomial, but to this linear function, but I'm comparing to this A linear function. So U epsilon minus U epsilon theta minus gradient U epsilon theta x plus epsilon k x over epsilon squared. So this will be smaller than theta 2 plus 2 alpha. So here the main point is uniformity in epsilon, but only for epsilon sufficiently small. That makes sense because you're using the limit equation, and the limit equation can only give you information if epsilon is sufficiently small. And and you have an estimate, which is a comparison between U epsilon and a linear polynomial at 1 scale theta. So, so I will prove this this lemma. Yeah, maybe I think I can erase the equation. So there. So the first step in the proof. So step 1 in the proof is to fix theta and alpha. So to fix theta and alpha, you need to look at the limit equation. So what is the limit equation? So we know that will converge to some will converge to some problem, to some elliptic problem with some matrix A bar. And A bar is constant. And elliptic, so A bar and bounded by L. So I will have some matrix in this class of constant functions with ellipticity constant lambda and L. So it's important that my constant will be uniform in this class. And for this equation, so it's B01, B01 half, a smaller ball because I will only, so okay, so I'm assuming here an L2 bound, so I need more compactness, stronger compactness to pass to the limit, because I was assuming W12 bound in the lemma about weak convergence. So I will use Kyoto inequality to get bound on the gradient. But using Kyoto inequality, I'm reducing the ball. So I will work on a smaller ball, B01 half, for the limiting equation. But once I have the bound via Kyoto on the gradient, I can use a Relish compactness argument and get compactness in L2 of U epsilon. So I look at this equation, and regularity theory tells me that U bar is C2 in B0 1/4. So by Campanato, I know that, so okay, so U bar is C2 means that gradient U bar is C1. And I have a characterization of what it is to be in C1 in terms of Campanato. Because the Campanato lemma works for alpha 1 included. So I've read the characterization of this. So I have that gradient U bar minus the mean of gradient U bar. So the integral over B 0 rho or theta of but this I know is smaller than theta, a constant times theta squared. This I know from Campanato. And for simplicity, I will center all my balls at 0. Okay, so another comment is here I want to prove Lipschitz regularity in the whole ball, but for simplicity I center all my balls in 0. And you can do the same arguments I will do here by centering the ball at the balls at another point in B012, and do exactly the same arguments to get this Lipschitz estimate at other points. But I will focus on getting this Lipschitz estimate at the point 0 only. But the difficulty is the same, so I'm not hiding something, just technical. So this I know from Campanato. But now I can use Poincaré's inequality to get that, so I will get, so on the left hand side I will get u epsilon, so u bar x minus u bar theta minus gradient u bar theta dot x square b0 theta. And now, since I'm using Poincaré's inequality, I have a constant here which depends on theta, so I have a theta squared, and here I have 2 plus 2. So this constant C, now I will choose, so I will take alpha strictly smaller than 2, and I will choose theta sufficiently small so that C times theta 2 plus 2 is strictly smaller than theta 2 plus 2 alpha. And this constant C only depends on the lambda and on the L. Okay, so in the end, the theta will depend on the lambda and the L. But this is fundamental in order to be able to do some contradiction argument.
Alpha is less than 2. This alpha is 0 point something. It doesn't hold this inequality.
Yeah, alpha is strictly less than 2, but in the end you will get here the same alpha here. But this is a C1 alpha improved estimate. So this is actually better than the Lipschitz estimate we are trying to prove. So the idea is that on these large scales, you will get actually better than the Lipschitz bound, but you will get a C1 alpha bound. So the second step of the proof is the contradiction step. And this afternoon we'll see exactly the same scheme, but for the Navier-Stokes equations. So, so for the proof by contradiction, you assume that there exists epsilon k going to 0. A sequence of AK matrices in A per L lambda, and a sequence of solutions to the equation with oscillating coefficients in B01. And you assume that the bound on UK in L2, so you assume compactness in L2, but the conclusion of the lemma is false. So you assume that simultaneously you have this and the mean over B0 theta of UK minus UK theta minus gradient UK theta x plus epsilon k kk x over epsilon k that this is bigger than 2 plus 2 alpha. So the oscillation So the comparison between this and a linear polynomial again. Linear A-harmonic polynomial. So from this bound you will get compactness, as I told you. So, so by Cacciopoli, you get that UK is bounded in uniformly bounded in W12 of the smaller ball. And so from this you get that UK, so now we can directly apply the lemma. So by the lemma about weak convergence. You have that UK is converging strongly to U bar in L2 of B0 and gradient UK is converging weakly to gradient U bar in L2 B0 and moreover U bar solves the homogenized equation. Okay.
So if you take alpha is less than 2 and choose theta is bigger than 1.
No. Theta is between theta, I forgot to say, is between 0 and 1/2. So you take theta very small, so that this right-hand side, left-hand side is smaller than the right-hand side. I'm sorry? Sorry. What did I say? No, I was meaning less than 1. Yeah, sure. Thank you. I was confused because of the 2 here. And, okay. Yeah, so it's alpha less than 1. Okay? Sorry for that mistake. Thank you for noticing. Okay, so you take alpha less than 1. I can manipulate it there. Okay, so so by the weak convergence, you also have the weak convergence of the means. So UK theta converges to U bar theta. So this is just by weak convergence, and the same for U bar UK bar. Okay, and you also have that this term here converges strongly in L2 to 0 because of the epsilon k again, and since the corrector is bounded. So epsilon k, kk, this goes again strongly to 0 in L2. And in this way, you can pass to the limit in this inequality, and you obtain that theta 2 alpha, 2 plus 2 alpha, is bigger than less or equal to so I pass to the limit here, and I get that this is less or equal to U bar x minus U bar theta minus gradient U bar theta dot x square B0 theta plus O of 1, small o of 1. But this I know is contradicts, so contradicts, because this we know is smaller than theta 4, basically, c times theta 4, so contradicts the fact that contradicts the choice of theta. because you get here theta 2 plus 2 alpha is smaller or equal to c theta 4. So by our choice of theta, this is not possible. And this concludes the proof. So it's actually very simple once everything is set up correctly. Okay, so so now I'll do the second step, which is the iteration. So step 2 of the proof of the Lipschitz estimate. So you notice in the first lemma that epsilon has to be between 0 and epsilon naught. So that's a restriction on epsilon. And when we will reiterate, this restriction will appear again. And that, in the end, will limit the scales on which we can prove our uniformity. So I let alpha, theta, and epsilon naught be given by the lemma above. And so for all A in A per of L lambda, for all weak solution 2 star, U bar epsilon square. So the mean, again, bounded by 1. So I take a family of solution which has some compactness properties, implies that for all k in n, k bigger than 1, there exists A epsilon k and B epsilon k, such that A epsilon k, so these are constants. So this is in R, and this is in R. This is in R, and this is in RD. So A epsilon k and B epsilon k are bounded by theta minus d over 2, 1 plus theta alpha plus theta alpha times k minus 1. And their inf, or let me write it like this first. So the mean on B0 theta k of U epsilon minus A epsilon k minus B epsilon k dot x plus epsilon k x over epsilon square is bounded by theta 2 1 plus alpha k. Okay, so let me pause a minute to explain this result. So, so here, and this I forgot to say, holds. But this is actually important. For all you, so here I forgot to say that for all epsilon between 0 and theta k minus 1 epsilon naught. So this is actually an important restriction. We'll see where it comes from in the proof, but don't forget to write this in your notes. So here we're comparing u epsilon for epsilon sufficiently small to a linear polynomial again, a linear polynomial. And we are proving that this oscillation, this is some kind of measure of oscillation, goes to 0 very fast when k tends to infinity. So it goes to 0 very fast with k. So let me just write this in another form. So this, you see that this is bigger than the inf of all A in R and B in RD of U epsilon x, so of the in bar d0 theta k minus A minus B dot x square. Okay, so if you don't like the A epsilon k and B epsilon k. So the iteration
may I ask, I cannot see on what domain do you integrate that?
so the ball centered at 0.
The yellow one.
Are the same.
Oh, okay.
Yeah, sorry.
Thank you.
So the iteration would be easier. If there was not, if no correction k, kappa, okay. So it would be easier, and in that case, we would have A epsilon k is equal to the mean of U epsilon on the ball of radius theta k, and B epsilon k would be the mean of gradient U epsilon on the ball of radius theta k. Okay? But here, since we have the chi, there is some correction, and this bound here is very important if you want to actually use this result in the end to get the Lipschitz estimate. Because to get the Lipschitz estimate, you will compare U epsilon to constants and put this on the right hand side, and you have to estimate this right hand side. So you need a bound on B epsilon k. All right, so I will prove this iteration lemma, and so the iteration is on k. And so for k equal to 1, it's simply lemma 1, or lemma of step 1. And you notice that you can estimate the mean of U epsilon theta by just applying Hölder inequality. This will be theta minus d over 2. Theta minus d over 2 times the b0 theta of U epsilon square. 1/2. So this just bounded by this, basically. And the same thing for the gradient. So this is bounded by 1, but for the gradient you will get some constant. Okay, so this theta minus d/2 is the one appearing here. And we'll use that for recursively also. So for k bigger than 1, we'll consider, so we'll start from this, or this bound. So we'll assume the bound for k, for some k bigger than 1. And we'll prove it, or for, let's say, k minus 1 bigger than 1. And we'll prove it for k. So we'll consider the auxiliary function u epsilon of x, which is the rescale thing. So I will consider u epsilon of theta k minus 1 x minus a epsilon k minus b epsilon k theta k minus 1 plus epsilon chi theta k minus 1 over epsilon x square, over theta 1 plus alpha k. And this function has good properties. So this function first has, if I integrate it over b01, this is smaller than 1 square. So why is that? Just because of the recurrence hypothesis. This is simple to check. Just make a change of variables and you will see that this is true. And u epsilon, moreover, is a solution of the equation. So minus divergence a theta k minus 1 x over epsilon, gradient u epsilon, is 0. And it's a solution of the equation because this is a solution of the equation, this is constant, and this is a-linear because of the corrector. So it's a solution of the equation. And now you want to apply the lemma 1 to this capital U epsilon. And so if you apply lemma 1 to this capital U epsilon, you get that for epsilon smaller than theta k minus 1 epsilon naught. So why is that? Because this is like, if you want your new epsilon tilde, the scale at which you have the oscillations. And so this epsilon tilde has to be smaller than epsilon naught in lemma 1. So you get this condition. So so you apply the regularity theory, the first lemma, and you get that 2 plus 2 alpha is bigger than the mean over b0 theta of u epsilon minus all their quantities for u epsilon, which I don't write again, but and this is equal to 1 over theta 2 plus 2 alpha k minus 1 times the mean over b0 theta k of u epsilon of x minus a epsilon of k minus b epsilon of k square. Okay, and with a epsilon k, which is a epsilon k minus 1, plus theta alpha, so this is also just a simple computation, alpha k minus 1 times the mean of U epsilon theta. And the same thing for B epsilon k. Okay. So, so you have the recurrence hypothesis on the A epsilon k minus 1, the B epsilon k minus 1. And the U epsilon, because it satisfies this bound, it also satisfies those bounds. So you can get the result for A epsilon k and B epsilon k at step k by just using the bound for capital U epsilon. Because it satisfies exactly the same a priori bound than the small U epsilon. So you can do exactly the same computation here as you did for U epsilon. So in the end, you get the bound for A epsilon k and B epsilon k. And this here, if you put this in the left-hand side, this will give you the rate decay, which is here. Okay. So this is the conclusion of the iteration step. So, I mean, there are some computations I'm hiding, but their essential idea is here. So, I will just take 5 more minutes. I mean, if you need to leave, or you can of course leave, but I just want to talk about Liouville theorems in 5 minutes. So it's quite clear how this now, how the Lipschitz estimate is a consequence of this improved C1 alpha estimate. Because here we got the estimate for all scales between epsilon and 1/2. Because of the restriction here, we have theta k minus 1, which is to think about the scales rule at which you can prove an estimate, which is bounded by epsilon over epsilon naught. Okay, from below. Because of this. And so it's clear from this that the scales for which you can prove this improved bounds are the scales between epsilon and 1/2. And below that, because if you want the whole Lipschitz estimate, you need to estimate below this scale epsilon, you will apply classical regularity. So that's what I meant with improved regularity taking place on scales epsilon to 1/2. And okay, and actually this improved regularity now is the key tool for getting Liouville estimates. Liouville type theorems. So I'm considering now the equation in the whole of OD. So I'm considering solution to this equation in the whole of OD. So you know that if I didn't have oscillating coefficients, constant coefficient, I have Liouville theorems which characterize the polynomial solution of this equation. It's so looking at this equation in a big ball. So looking at this equation in B0 R for some large R is somehow equivalent to asking the question about uniform estimate for small epsilon. Because just doing a rescaling, taking epsilon is equal to R minus 1, I have an equation with highly oscillating coefficients in a domain which is B01, which is fixed. So this is the key insight of how to use this estimate uniform in epsilon. So now I take in RD. So I will be able to take arbitrarily large balls R, B0 R. So the theorem is the following. So if there exists constant C and sigma in 0, 1, such that for all R, let's say bigger than this here, the mean of U squared over B0R is bounded by CR to sigma. So if I have a bound on the growth of U squared for sufficiently large R, then there exists A in R such that U of Y is equal to A for all Y in R. So U is constant. So actually here I can allow U to grow I mean it does not need to be bounded, it can grow sublinearly. So slower than a linear function. Sorry. And the second part of the theorem is if there exists C and sigma again in 0, 1, so C is bigger than 0 and sigma is in 0, 1, such that for all R bigger than 1000, the mean of U squared over B0R is smaller than R2 plus 2 sigma. So I'm assuming that the growth of U is, can be linear but also sub-quadratic. And in that case, then there exists A in R and B in RD, such that U of Y is equal to A plus B dot Y plus Ky Y. For all Y in R. So this characterizes the solutions to this equation which grows sub-quadratically at infinity. And this tells me also the remark I made at the beginning of the lectures, that the constant and their A linear functions are the building blocks of regularity theory. So to prove this, I will just write one estimate, and I will let you think about how this estimate enables to prove the claim. So, I'm looking at the solution of AY gradient U in B0R. Okay, for large R. And then there exists a constant C depending on dimension lambda L alpha, such that so for all solution to this equation, the inf of A in R and B in RD of the mean of over B0R of U of Y minus A minus B dot Y plus Chi this is bounded by C times R over capital R 2 plus 2 alpha. B0 R. So this is just a rescaling of the previous estimate. So this holds for any R between 1 and R over 3. So this is just a rescaling of the previous estimate of lemma 2. And once you have this estimate, then you can use the growth of this integral here by assumption, and let R, capital R, go to infinity, and get the result. Okay, so I conclude the proof here, and I stop this lecture here. So this afternoon I will talk about fluid mechanics and Navier-Stokes equation in 3 dimensions. Thank you.